Hello everyone, welcome to my channel. Today, I would like to discuss the topic of polynomials factorization over the rational numbers, the real numbers, and the complex numbers. When factorizing polynomials, I believe many students encounter such problems. However, these problems are closely related to the choice of number fields. I hope that after watching this video, you will have a good understanding of these problems. Okay, let's begin. First, let's briefly review what factorization is. In general, factorizing a polynomial means expressing it as a product of two or more polynomials of lower degree. For example, if a polynomial fx can be written as fx equal to gx times hx, then we call gx and fx factors of fx. Let's look at two basic examples. X squared minus 1 equal to x minus 1 times x plus 1, and x squared plus 5x plus 6 equal to x plus 2 times x plus 3. These seem very simple and straightforward, right? However, are all factorizations as obvious as this? Now, let's consider two more thought-provoking examples. First example, factor s squared minus 2 over q. Many students would write like this. They just simply use root 2. However, it is correct. Obviously, it's wrong. Then, let's find why. From a calculation perspective, this is correct. However, look carefully. The question requires us to factor it over the q. So, this answer is incorrect because root 2 is not a rational number. Therefore, over q, x squared minus 2 cannot be factorized. However, if we change the requirement to factorization over r, then it works, right? Because root 2 is a real number. Okay, second example, x squared plus 4. Many students do some calculation like this. Let x squared plus 4 equal to 0. Then they get delta equal to minus 16. They say this quadratic equation has no real roots. So they think these polynomials can be factorized. It is correct. This is also incorrect because they only considered real numbers. However, over C, it can be written as x squared plus 4 equal to x plus 2i times x minus 2i. Okay, then through these two examples, we discover that in factorization, many errors are not due to calculation mistakes, but to overlook the number field required in the problem. This is why we compare factorization over Q, R, and C. So, what does it mean to factor a polynomial over a number field F? Let's take a look at its definition. A polynomial can be factorized over a number field F if it can be written as a product of polynomials of lower degree, and all coefficients of these polynomials must belong to F. Okay, please pay attention to the last sentence. It is important. That is to say, over Q, all coefficients must be rational numbers. Over R, all coefficients must be real numbers. Similarly, over C, all coefficients must be complex numbers. Now, let's use a specific example to see how it works. Example: analyze the factorization over the polynomial fx equal to x power 4 minus 4 over q, r, and c. To start, let's look at the factorization over the rational numbers q. First, we factor it into this form: x to the power of 4 minus 4 equal to x squared minus 2 times x squared plus 2. Now, we let x squared minus 2 equal to 0 and x squared plus 2 equal to 0. We find that their roots, root 2 and root 2i, are not rational. However, we notice that the number field here is q, so we can only use rational numbers to be the coefficients. So, neither x squared minus 2 nor x squared plus 2 can be factorized further over q. So, the solution is x squared minus 2 times x squared plus 2. Next, let's see what differences there are over the real numbers r. Compared to q over r, we can use irrational numbers, but we still cannot use imaginary numbers. Therefore, we can factor x squared minus 2, but x squared plus 2 remains irreducible. So, the solution is x minus root 2 times x squared plus root 2 times x squared plus 2. Finally, let's look at factorization over the complex numbers c. Here, we have no restrictions or coefficients. Therefore, we can completely factor the polynomials. So, the final result is just this. Okay, then let's put these three factorization situations together and check them. We find that the same polynomials can have completely different factorization forms over different number fields. And as the number field becomes larger, the possibilities for factorization increase. So, let's find why. Let's go back to the definition we just talked about. As you can see, you find that compared to Q, R allows the use of irrational numbers, and compared to Q or R, C allows the use of imaginary numbers. Then, we have already known these three number fields have this kind of relationship. Q is a subset of R, which is a subset of C. This means that as the number field becomes larger, we have more numbers to use as coefficients, and thus the possibilities of factorization increases. That's exactly why the factorization becomes more and more complete when we move from Q to R to C. Now, let's summarize what we have learned. First one, factorization must be performed within a given number field F, and all coefficients of the factors must belong to F. Second one, as the number field expands from Q to R to C, the possibilities for factorization increase. So, the next time you perform polynomial factorization, first ask yourself, which number field am I working in? That's all for today. Thank you for your watching and listening. See you next time.